Welcome to Breadboarding. In the previous video we tested out some buffers and latches, and we also tested out our bus rails here, which is the stripboard bus rails with our various rainbow DuPont connectors. And we were able to run this using a variety of different crystal frequencies, and the highest frequency we managed to get working was a 66 megahertz one, and this meant that our A0 sort of simulated address line was a signal of about 16 megahertz. But this was a signal actually coming out from this probe over here, and you can see that we were still getting fairly reasonable sort of signals out of this. So this is the 14th in the series of how to use breadboards and retro digital electronics. And in this video, which should be the last in the series, I'm going to cover all the TTL logic that appeared in the IBM PC and PC-XT, and I'm going to do an analysis of the differences between the PC and the XT, and also be looking a little bit at the XI8088 where these differ. So the IBM PC was released in October 1981 and the PC-XT was released in March 1983. They both used the Intel 8088 version of the 8086 processor, and this allowed to have up to 1 megabyte of address space, so this was 20 address lines, A0 to A19. Now the difference was that the 8088 only used an 8-bit data bus, whereas the 8086 used a 16-bit data bus, but this made it a bit simpler and cheaper to actually build the computer with the 8-bit data bus. Now the PC and the PC-XT are very similar apart from the following differences. So the PC had a cassette interface and at release only had 16 or 64K of RAM, whereas the PC-XT had a hard drive option and came with 128K to start with. The PC had 5 ISA bus expansion slots, whereas the XT had 8. And the PC came with PC-DOS1 or MS-DOS1, and the XT came with PC-DOS2. So this has been enhanced to actually know how to handle hard drives and folder structures. So we're going to be comparing the documentation for the PC from April 1984 with the March 1986 PC-XT documentation. And part of the reason for doing this is that the diagrams are a bit clearer in these versions. Some of the earlier versions weren't quite as clear. And it also allows us to compare the 64K/256K configurations of both the PC and the PC-XT. So I've taken this one from -0degrees.net. It's a really useful site for early IBM PCs. I've used this in some of the earlier series of videos, and in particular, if you want to look at all the information on here about the original PC and the PC-XT, there's a lot of good diagrams and things, and also access to the documentation through here as well. So this is the document, and the location of the schematics differs slightly by version of the document. So I've taken screenshots of the diagrams here for sheet 1 to 10 from the PC. Then the PC-XT is also -0degrees.net, and there is the 5155-5160 technical reference here from March 86. And this is at page 56. And you'll notice, in fact, in this document, there's two versions of the diagrams. There's one for the 64K, 256K system board, and there's another one for, I think it's 256K, 640K, so the slightly larger memory series. But because these two are the same, I'm going to be comparing these two. So let's dig in. I'm going to go fairly quickly through here. I'm just really going to be calling out the main differences between the two versions. So the PC has got the blue titles here, and the XT will have the yellow titles. Now you'll see that when you look at these, what I've done here is just called out where there are differences between the two versions, and occasionally there's also mistakes. So for example here, the XA0 is the X-bus address line. It shouldn't have a bar over the top of it, for example. And also it was interesting in that this particular chip, the interrupt controller is connected directly to the processor bus and not via any buffers, whereas we'll see in the XT it's connected to the X-bus. And there's also some differences here in that some of the control signals here, the S2 processor signal actually goes to the logic for the hold acknowledge, whereas we'll see with the XT it doesn't. So what we've got here is the 8088 processor, the clock controller, the bus controller, The interrupt controller is also here. This is the socket for the maths coprocessor, which you generally don't bother with because early versions really wasn't much software that made use of the maths coprocessor. And from the 486 onwards, then the coprocessor was included in the chip. And then we've got bidirectional buffer for the data bus, and then 3 lots of address latches, and we covered the latches and buffers in the previous video. So then the XT, you'll notice that for this, the interrupt controller is now connected to the X bus here, the X data bus, not directly to the AD bus, multiplex bus here. And you can see this diagram probably isn't quite as clear. It almost looks like it was hand-drawn, but we've also got the clock controller, bus controller, coprocessor, and again we've got our various buffers and latches in here. Now there are a few differences. We'll come to slot 8 a little bit later on, but some extra signals needed for the logic to handle the slot 8, which was a special slot on the PC-XT. The PC only had 5 slots, so it didn't really count for that one. And you'll see here that there is no S2 signal coming on the bus control signals. There is no S2 signal going out of the hold acknowledge. But you'll see that they're pretty similar. There's a few minor differences. The label for here should be XA0, but it's AX0, and there should be a non-maskable interrupt label there as well. So there are a few mistakes on these diagrams as well. So the clock control logic, I'm not going to go through the contents of here because it's fairly complicated, and I have done this in a number of the videos around DMA, for example. And if you want to know what a lot of this logic does, if you go to -0degrees.net, then there's explanations of things of quite a few sections of these. But the main difference is here, the S2 signal we had on the previous slide is passed into this logic, which is all to do with the handling of DMA requests. And in fact, the request for DMA is actually active low in this particular diagram, whereas when we go to the XT, you'll see that the request for DMA is actually active high. We don't have the S2. And there's also an extra condition added in here in that there's an extra bit of logic here to do with the DMA chip select to prevent the DMA request from starting if the DMA controller is actually in the process of being updated. And this was a change that was done in some of the later XT revisions. And up here, there's a couple of extra signals at the top that only appear in the XT. Other than that, virtually all the other signals, input and output, are the same as far as I can tell from a sort of a moderate amount of effort comparing these. So then we go on to the I/O and address decoding. Now on this one, which is for the PC, you can see up here, this is where we get the DMA interrupt controller, timer, and the parallel port interface, I/O signals, various other selects, so the ROM address select, the RAM address select, and there's a number of chip selects on the PC used for the system ROMs. Now you'll see the address decoding for the RAM here is actually just using a decoder, a 74LS138, which we covered in some of the earlier videos. But when we go to the XT version, we'll see that this 138 has actually been replaced by this 24S10. Now, it's a bit difficult to find information out about this, but this is actually a bipolar programmable read-only memory. So this was effectively a ROM chip that was programmed with the various rules in here to provide the outputs here. So I guess it was an early version of a programmable logic device. I haven't seen any of the rules that are actually used to generate in here, but you could probably work it out from the inputs here and what we actually need for the RAM select. So the planar RAM 0 and RAM 1 are different from the original PC. And we can see here that the chip select 2 to chip select 5 are actually used on the PC, only chip select 6 and 7 are used on the XT. Other than that, it seems to be largely the same. Then we get to the DMA controller. Now the DMA controller is virtually the same between the two versions. We're going to be coming back to the 74LS670 a little bit later, and this is a 4-bit register with 4 addresses, which is used to provide the top address line. So the DMA controller can only address 64K or A0 up to A15, and so A16 to A19 is actually provided by this register. And the logic around here is a little bit strange, particularly to do with how the DMA acknowledged 2 and 3 lines are actually used to control the address where the data is actually pulled from. The XT has this signal active high, whereas the PC has it active low. And again, the only difference really here on the XT is the fact that this signal is actually active high and it's active low on the PC. So the X bus was a section of the PC bus which was separated for the system input-output devices, so things like the timer, DMA controller, interrupt controllers, all those sorts of things were on a separate bus. Partly, I think, because the main address and data buffers probably weren't able to drive all of the expansion sockets by default, and so this X bus was actually separated off, and we had both the address and the data bus. So this is some of the buffering for the X bus, but we've also got a number of ROM chips here. So on the PC, there were space for up to 6 8K ROMs. And the DAC 0, the DMA acknowledged 0 line, was actually used for doing the dynamic RAM refresh. On the PC, this is active low. On the XT, it is active high. And we can see here that with the XT, because it's a number of years later, then the 8K ROMs have been replaced by 2 32K ROMs. This signal here is only on the XT, and you can see here that the DMA acknowledged 0 is in fact active high. Now, there's a couple of extra signals that we covered on the first slide. So the interrupt acknowledge and card selected is related to the handling of the slot 8 ISA bus card, and it actually needs to include some extra conditions to handle some of the buffer directions, which we'll come to a little bit later. But the PC only had 5 slots, so it didn't have this complication. Interestingly, that in later versions, and this slot 8 handling was dropped in the PC-80 onwards. So then we come to the parity multiplexers and buffers. Now, there's not a lot of difference between the two versions here. Basically, you've got some multiplexers here which take the address lines and multiplex them down to the rows and columns needed to access the RAM. Now, this diagram shows 64K RAM. So if we had a 64K PC, with this version of the motherboard, you'd just have one bank of RAM would be populated. So bank 0 was generally soldered into the motherboard, and bank 1, 2 and 3 would then have sockets, and you could then expand them. So if all 4 banks of 64K RAM were populated, we'd have our 256K. I think for 64K, only bank 0 will be populated, although later we'll see there are some 16K chips, which I don't think are quite right. Again, there may be a mistake actually in the original diagrams, because these particular boards only use 64K RAM chips. And again, not a lot of difference between the two. So here is the parity chip. This is a 74S280, and this basically calculates the bit 9 for the parity on saving, and also then on reading the RAM, then also calculate the parity. And the signals here are used to go off to the parity checking and produce sort of non-maskable interrupts if there's a parity error, for example. On all the Breadboard PC and the XI8088, then we don't worry about parity. So a lot of the parity checking I've skipped over in the Breadboard PC series. Then we come to the PC RAM board. Now, as I said, from what I can tell, and -0 degrees had quite a lot of information on this, then the 64/256K board would only have bank 0 with 64K in, and the others would be empty. So I'm not quite sure why these have 16K. Perhaps they just didn't update the diagram before it was published. They really should be 64, I believe. And you'll see that in the XT version, then in fact this bank 2 and bank 3 are both 64K, and obviously they have the same configuration, so I suspect the previous slide was just a mistake. So this is one of the main differences. So this is the system timer, speaker and RAM DMA refresh. And so what this timer chip does is it generates a DMA request 0, which is used to initiate the dynamic RAM refresh. There's also the output here for the system timer interrupt, IRQ0. This chip here drives the speaker output, so it's a dual peripheral driver. It's just got effectively some higher power outputs on here to be able to drive external outputs. And the main difference between the PC and the PC-XT, certainly in this area, is that this had a cassette tape interface. This would allow loading and saving programs to the cassette tape, and the built-in BASIC was a cassette BASIC. It would only allow loading and saving to cassette. If you wanted BASIC able to read and write floppy disks, you'd need to use the version installed on PC-DOS. And you'll see that the motor off is coming from one of the parallel peripheral interface, and is one of the outputs being driven by this chip here. So on the XT, this section was removed. So you'll see here there's a blank bit down the bottom here, but there was a bit of extra logic to do with the read and write of the timer here. So there's an extra bit here that doesn't exist on the original PC. I suspect it was to solve some particular timing issues. Then we've got the PPI, so the parallel peripheral interface, and there's quite a few options here. So we've got the various dip switch options for configuring the memory size, display type, number of floppy disk drives. And over here we've actually got the original PC and PC-XT keyboard controller, and this was very much handled by this rather unusual shift register here. So it's a parallel in, parallel out shift register. I don't believe you can buy these anymore. They've certainly been discontinued for many years. You may well buy them on eBay, but there's no real point in buying them, because unless you have a PC or a PC-XT compatible keyboard, then it won't be able to talk to anything. And so this is very much a hardwired keyboard interface, and this was replaced in later versions with the Intel 8042 microcontroller. And in fact, in the Breadboard PC and XI8088 designs, then there is a PS2 compatible keyboard controller that we use. And again, you'll see here very similar. Some of the dip selections will be slightly different, but pretty much the rest of it is the same. Then on the original PC, we only had 5 ISA expansion slots, and the B08 was just reserved. There was nothing assigned to it. Then we look at the PC-XT, and again we can see that the B08 was reserved here, and this was for the slots 1 to 7. But then on the slot 8, which was actually connected to the X bus, so you can see here this slot was actually on the X data and the X address bus, whereas the other ones are on the main data and the main address bus. So there was a bit of a difference in that, and cards that actually were going to be plugged into this particular connector had to enable this B08 card selected line, and this was used to configure some of the buffer directions that were needed for cards in this particular slot to work. Fortunately, this special slot 8 was dropped in later versions of PCs, so certainly PC-80 onwards we didn't have to worry about that. So that's a quick blast through comparison between the PC and the PC-XT. They were very similar with the exception of the cassette tape interface. Then there were only a few minor changes here and there, slight difference in the way how the logic was configured, but other than that there weren't too many differences. So in addition to the original PC and the PC-XT, I've also analysed the XI8088. So this was a hybrid design that Sergei Kiselev produced, and there is a PCB version of this. And this design was using static RAM, so no dynamic RAM refresh, which is recommended for any sort of breadboard PC. You don't want to be messing around with dynamic RAM. It also included a PS2 compatible keyboard and mouse controller, made it a lot easier to integrate with modern keyboards and mice. Included a real-time clock that was first introduced in the PC-AT, had a simplified port B rather than the 8255 parallel peripheral interface. It had dual interrupt controllers so that you could have the mouse and network adapters, for example. It also included some aspects of the 16-bit ISA bus for certain ISA cards. And I also looked at the CGA video card as well, so there is actually a KeyCAD project with the original CGA video card design, so I've actually been able to export the bill of materials from both the XI8088 and the CGA video card. So what I've done is I've gone through all the diagrams and I've created a spreadsheet from the original PC. So these are all of the chip identifiers from the original PC diagrams, cross-referenced which sheet they're in. Then produced a summary of those. So the green ones are the ones which are logic gates. So we've got about 21 logic gate types here. Then I've also done the same for the XI8088 and the CGA video card. So the CGA video card has a KiCad schematic for it, so you can actually go through the whole schematic and export all of the bill of materials. Done the same for the XI88 as well. And that then has resulted in a consolidated list. So this basically shows all the different chips, for which there's 33 different logic chip types used across the IBM PC, PC-XT and the CGA card. And I've color-coded them into the different groupings that we've used in the series, so logic chips, buffers, counters, shift registers, those sorts of things. And so I'm going to go through those chips and cover off any that we haven't covered so far in the series. Sort of the basic logic gates, we've covered the majority of these. So you covered the AND gates, the NAND gates, the multiple input, triple input NAND gates, hex inverters, and also the NOR gates as well. We covered those in a number of the earlier videos. The only thing we haven't really covered is the inverters, but with open drain or open collector outputs. So we'll come back and cover that a little bit later. We've also done the triple input NAND gates, the quadruple OR gates, the XOR gates, and the 4-input NAND gate as well. We've covered all of those. However, the open collector NAND gates we haven't really covered there, although the inverter one would kindly cover that, or the and the 51, which is a bit of an unusual one, sort of a combination of gates. This type of chip we probably replace with a program or logic device these days. Then on the flip-flop side of things, we covered the D-type, we covered the JK, and also the D-type hex with clear, and the quadruple D-type with clear and the inverted outputs, and also the 273 octal flip-flops with the clear input. Then on the decoder side of things, we covered the 138 and 139 decoders, demultiplexers. We also briefly covered the 158 and 157, and also the 153. We didn't really cover the parity generator because we weren't really worrying about parity because of using static RAM. So we'll come back and look at that. Then on the buffers side of things, in the previous video, we kind of covered this simple one here. And then the 244 is used quite a lot in the original PC, but we're generally going to replace these with the 541, which we covered in the earlier videos. The octal bus transceivers we covered, and the 374 and 574s, and the 573s, and then the 670, which is a 4-bit register with 4 addresses, we haven't really covered, so we'll come back to that as well. And then on the counter side of things, this particular one, the 322, is used for the keyboard controller. That's obsolete. You can't really get those anymore, and the diagrams aren't even in the TI datasheet anymore. And the main recommendation I've seen is you construct one of these from a program or logic device should you want one. But invariably this has been replaced now by the PS2 keyboard mouse controller, so not really going to worry about that too much. We covered the divide by 12 counter, the synchronous binary counter, the parallel shift register, parallel load shift register, and the serial in parallel out shift register. This counter here we didn't really cover. I haven't got one of these, but it's very, very similar to this, just without the ability to preset the inputs. Now we're going to go through and look at those chips where we had the question marks, where we hadn't really covered them previously. So I'm going to start with the 74LS06 hex inverter with open collector or open drain outputs. So we covered what open collector, open drain was in some of the earlier videos. It's probably just worthwhile going to the datasheet and remind ourselves of a couple of the points about these chips. So this is 74LS06 hex inverter drivers with open collector high voltage outputs. It's worthwhile noting that the LS06 device can actually deal with voltages of up to 30 volts and can also sync up to 40 milliamps. And if we just scroll down to the diagram here, you can see that we don't actually have the totem pole 2 outputs like we have on the normal chips. We only have this single transistor here, which if we actually tie a load to a higher voltage, whether it be 5 volts or can be up to 30 volts, then it's able to connect that voltage to ground through this output transistor here. And if you just have a look at those diagrams alongside one of the standard 04, so this is the output stage for the 74LS04, and you can see this has got the totem pole output. We've both got the pull up to high voltage and pull down to low voltage. You can see here that this part is really missing. And in order for us to actually get an output here, we wanted to put an oscilloscope or a logic probe on here. We just didn't do anything else, so we wouldn't actually see anything on here. And what you actually need to do is to put some sort of pull-up resistor either to 5 volts or to whatever voltage you are using. And you could use this, for example, for driving LEDs, or driving, say, a circuit that required 12 volts input, or even just for converting from TTL logic levels to CMOS logic levels, by connecting this to whatever the voltage that the other logic is running from, then you'll be able to convert the output of this TTL going into that CMOS. So this particular chip, just one thing worthwhile noting is that this is a particular one which is capable of doing high voltages. Not all open collector chips are capable of doing high voltages. And when we come on to the next one, so this is the positive NAND buffers with open collector outputs. So this is very similar. It has open collector outputs. If we go and have a look at the datasheet, there's an open collector outputs, but it isn't a high voltage. And so if we have a look here for the 74LS38, we can see the maximum output voltage there is 5.5 volts. But in general, we can use open collector outputs if we're needing to have multiple chips able to pull a control line low, for example. Then we can use the open collector outputs to all be connected together. And as long as we have a pull-up resistor, then in fact, multiple outputs can drive one input. Let's move on now to the 74LS51. So this is a bit of an unusual one. If we go into the data sheet for this, it'll make it a little easier to see what it is. We would tend to, in the more recent projects I've done, I would tend to replace this type of logic gate with a programmable logic device. Is probably an easy way of doing it, but let's have a look at it anyway. This is just the and/or invert. So this is effectively there's different layouts depending on the chip series, but what we can see here, we've got 2 NOR gates, and then we've got a 3-input AND gate and a 3-input AND gate for this one, and a 2-input AND gate here. I think what this logic basically does, because you will only get a 1 out of a NOR gate when we have 2 inputs of 0. So if any of these inputs are 0 or these inputs are 0, we'll end up with a 0 coming out of here, and then we'll get a 1 coming out of here. So then we come to the 280 parity generator. Now, in fact, on the IBM PC, this was an S-series part, so it's a little bit faster. And the 9-bit parity generator is needed because you'll have the 8 bits of data plus the 9th bit, which is the parity bit. And when the PC stores data, it'll calculate the parity and store that in the 9th bit. And when we read the data, it will then read back the 8 bits of data and the parity, and will then check it. Just have a look at the data sheet for that. You'll see based on the number of inputs that are high, then this will determine whether or not we get the even parity or the odd parity output. You'll see here that we've got the A to H is the 8 inputs and the I is the 9th input. And in fact, you can see here for the speed, then the S series will do this in 14 nanoseconds, whereas the LS series will take 33 nanoseconds. So again, because the dynamic RAM accessing was quite speed dependent, then the PC used the 14 nanosecond part. Then we come on to this rather unusual 74LS322 shift register, parallel input-output shift register, and this was used in the PC and the PC-XT keyboard controller. As I said earlier, you're unable to buy these anymore, and what it basically has is a parallel in, so 8 inputs or 8 outputs, and the table here actually explains a little bit more about what's going on, but fundamentally the load is when the SP goes L, and when that goes low, then in fact the values are then effectively loaded into the registers, and then as the clock rises with these other settings here, then you'll actually get the values then be rotated coming out through the QH output here. And also, depending on if you're actually receiving data, then you can feed the data into either D0 or D1. You select which of those would be chosen based on the data select. So if we had data select low, then D0 would be feeding in here. And again, once you've actually done that, you can actually read the output off of the QA to QH can actually then be read. But this has largely been made irrelevant by the PS2 keyboard controllers that we use on the Breadboard PC projects and on the XI8088. Then we've got this 393 dual 4-bit binary counter, very similar to the binary counters we were looking at. There's a little bit different in that it is asynchronous to a certain extent, so let's just have a quick look at that. This data sheet covers a number of the different parts, but the one we're interested in is the dual 4-bit binary counter with individual clocks. There's a maximum frequency of about 35 megahertz. You can see here that the 393 goes all the way from 0 up to 15 with these outputs. Now, if you have a look at the logic diagram, you can see that in fact these are T-type flip-flops, and because the output of each flip-flop is feeding into the next input, then these are not synchronous, and so they may very well give you problems with spikes and delays between each of these outputs changing. So in general, I don't think we'd normally want to use these on modern projects anyway. To handle that. And then finally, there's this rather unusual one. It's the 74LS670, which is a 4x4 register. So this is basically a 4-bit memory with 4 addresses. We can have a look at that. So it's a little unusual in that it has 2 address input bits for reading, 2 address input bits for writing. Then we have the 4 data inputs, and then there's a separate 4 data outputs. And this is used with the DMA controller to provide the top 4 address lines, given that the DMA controllers used by the PC could only do 16 bits, and we needed a 20-bit address bus for the PC. You can see here that the data inputs are separate from the data outputs, and also that effectively the write address WA, WB is separate from the read RA and RB. I won't cover how this is used on the IBM PC because we'll handle that when talking about DMA specifically. So we've now covered all of the logic chips which are used by the original IBM PC, the PC-XT, the XI8088 and the CGA graphics card. So now covered pretty much everything I could think about to cover retro digital electronics. So basically from all of these videos we've done here, you should now actually have sufficient background knowledge to understand how most of the parts of the original IBM PCs and other retro computer projects work. There will be a playlist in the description below, so if you go to the playlist you'll be able to go through the whole series sequentially if you have missed out on any. And what I'm currently working on at the moment, the COMPAQ DeskPro 386 was announced on the 9th of September 1986, and it was the first PC to use the Intel 80-386, or became known as the i386, which is the first Intel 32-bit CPU. And this had a 32-bit data bus versus a 286 that had a 16-bit data bus and the 8-bit data bus for the 8088. It extended the PC-XT and the PC-AT and was backwardsly compatible with those. And in fact, the DeskPro 386 actually had better compatibility with the IBM PS2 range, which came out about a year later. And really the DeskPro 386 defined the ISA PC standards, which are the basis for most modern computers. There was a really good technical reference guide provided with the COMPAQ, and a lot of the circuit diagrams and background information is in there. Now I'm looking at using an Intel 8386 DX33, so this was a slightly later part, but I'll probably be looking at clocking this probably around about 16 megahertz to start with. The actual clock frequency for the processor will be about 8 megahertz. And the reason for skipping the 286 really was that there's not much interesting you can do with a 286 that you can't do with an 8088, but really a 386 is needed if you want to run Windows 3.1, Windows 95 and early Linux Slackware distributions. So the coming series I'll be doing a 386 based breadboard PC, so keep an eye out. If you don't want to miss out on that series, then please hit subscribe. And if you found the content interesting, please hit like. It just helps to make the videos available to more people. Thanks for watching.